Okay, let's move straight into an example here. So in this example, you should see the months, all right, the 12 months in the year. And next to the 12 months in the year is the roadbed soil modulus of resilience, or the resilient modulus that's associated with that month. And so you can see here exactly what I was talking about before, which is January and February have pretty high resilient modulus or moduli because hey, it might be frozen during that time, and the soil might be a little bit stiff. But you move on down to, let's just say, a more wet type of time or period, the modulus resilience decreases. And then you get into the summertime and more into the fall, it almost kind of stabilizes around 8,000. And so this is something that we know. What they ended up doing in this example is calculating the relative damage using that same equation that I talked about before. But I'll go ahead and put it up here again. So the relative damage equation is 1.18 times 10 to the 8th. And all of that is going to be multiplied by whatever the resilient modulus is for that month raised to the negative, don't forget the negative, 2.32. And so what you see in this column is the related resilient modulus that is calculated in that column. So for February, all they did was place 22,000 into here, ended up getting a relative damage, and they placed it right next to it. Okay, so that's a way that we could figure out how the soil is damaged relative to each month. In the end, they took the average. So they took the summation of all of the months, and then they took the average. And in order to do that, since it's 12 months, they divided by 12. Now, if I only give you 4, then you just need to divide by 4. Okay? But in the end, they ended up getting an average of, and I'll write it a little bit bigger, 0.133. So that's the average relative damage. So the natural question is, okay, what do I do with that average? Well, you put it right back into this equation and solve for MR. Or, as I like to do, just go ahead and rewrite the MR, the equation, so that you would have it handy for yourself. So just rearranging terms here, my resilient modulus is equal to my average relative damage divided by 1.18 times 10 raised to the 8. And then this needs to be 1 over a negative 2.32. Again, don't forget that negative sign there. And don't forget to raise it to that 1 over that number. So when I place this average value, average relative damage, into this equation, I end up getting the resilient modulus that is representative of the entire year and not just one portion of the year. What they ended up getting is MR is equal to 7,250 psi. So now, when looking at the natural soil or the subgrade, they're going to be designing with the understanding that the resilient modulus, or the stiffness of it, is equal to 7,250, not 5,000 because that would be an underdesign, and not 22,000 because that would be an overdesign. Okay, so in this example, I want you to determine the design resilient modulus for the roadbed, or also referred to as a subgrade. And what is given to you is the months throughout the year in which they were able to get readings for the roadbed modulus. And so you have the associated values for each month. But I want to know, what should the design roadbed or the resilient modulus be for the roadbed? What should I be designing for? Should I design for January or December? Well, we know that this term right here is the relative damage, and the relative damage helps us understand what the change in weather does to the strength of the roadbed, and by figuring out what the average is, we'll be able to determine what the design resilient modulus should be. So let's just go ahead and get started. The relative damage that is associated with the resilient modulus of 35,000 in January, so it's very, very cold, probably very stiff, it's going to be equal to 1.18 times 10 to the 8th times 35,000 raised to the negative 2.32. And that gives me a relative damage of 0.03386. Let's do it one more time, and then I'll just start filling them in. For May, you can see it's a big change, big drop off. It's not as stiff as it used to be. 1.18 times 10 to the 8 times 2,150. All of that is raised to the negative 2.32. Don't forget the negative. It ends up giving me a relative damage of 2.190911. Wow, in May, it's a lot more damage, relatively speaking, to the soil than in January, which makes sense. It's wetter here. All right, I'll just fill in the rest of these here. So for July, we have 0.621805. Then we have 0.394847. And then last but not least, we have 0.156815. Now I need to figure out what the average is, because the average is what I need. Because if I take the average relative damage, then I've really accounted for all the weather patterns and weather changes and soil changes that occur throughout the entire year, at least for the information that I have. So I need to get the average relative damage. Well, you know how to take the average. You take the summation of all of these. So I am going to add this to this to this to this to this, and I will divide not by 12 like we did in the other example, but I'm going to divide by 1, 2, 3, 4, 5. By dividing by 5, of course, I'll get my average relative damage, which I've already found to be 0.673553. I'm not done yet, because I wanted to know what the design resilient modulus should be, so that when I design for my pavement, my subgrade, that lowest level, is as realistic as possible, accounting for everything that happens in the year. So I need to take that average and put it in here, and then recalculate a new modulus of resilience. Like, you could take the average of all of these and you end up with a much different number. You should try it and see what happens. But I'm going to take the average here, average relative damage, place it into this equation, and then calculate my modulus of resilience. So that is 0.673553 divided by 1.18 times 10 to the 8. I'm raising that to a negative. Just to make sure, I want you to know it's a negative here. 2.32. And that ends up giving me something very close to 3.6 times 10 to the third. If you really want to be specific, you should get a resilient modulus close to 3.574. If it's not exactly on this number, it's because it had to do with some type of rounding difference in the way that we calculated it. So I hope that explains everything.